So what does this dsdt part mean? Derivative of s. S means a specific thing in that we've been using in calculus. S means position. What's derivative of position? What is the derivative of position? Yes, velocity. What is the derivative of velocity?
Acceleration.
Acceleration. So we're asked to describe the motion of that. So we're going to take a look at the graph. Okay. Because what it gives us is a velocity. Yeah. Now, it does ask me for time 0 to 5. X is now time. And that's not showing up on my graph at all. I'm just going to make this the X coordinates that it tells me. And I have no idea where this is. Did I type it right? I didn't take it. Okay. That might be the problem. Okay. So here it is on 0 to 5. How could I describe the motion of the graph? I might want that point where it intersects. I think it's 2, but we'll double check. No, it's not 2. So what is this graph? What is this particle doing? We can change the zoom a little bit, but
It's either getting closer or it's going further away.
so what is happening here when it equals 0? For a velocity.
Should not be.
It's not moving. So it starts negative, so it's going backwards until 1.255 seconds. It's decreasing its speed in a negative direction until it stops, turns around and goes in a positive direction at an increasing speed. That kind of makes sense?
Yeah.
Finding position from displacement. Oops. I didn't share that on the video. So this is the graph. Looks like that. Now I'll go back to our whiteboard. So it says, suppose the initial position of a particle S0 equals 9. We'll do this one. And this is my initial position. That's where it starts at. This is one-dimensional motion, so it's essentially moving on a horizontal axis. Okay. What is the particle's position? So we're using our same equation here. It asks for S of 1 and S of 5. Okay? So we know displacement or change in position I get by taking this integral. So S of 1 equals the integral from 0 to 1. I could separate the variables by multiplying each side by dt, but that's pretty straightforward. And then I have to add my initial position. I'm writing that in front so it doesn't look, so it can't be mistaken for part of the integral. Now I'm going to go to my calculator. You're going to use your calculator a lot in this chapter because I don't want to integrate that by hand. And 9 plus, to integrate on the calculator, do menu calculus numerical integral. And here I can use either a t or an x. Doesn't matter. It's at position 5.33. If I wanted it 5 seconds and copy and paste, all I have to do is change the upper bound. It's now at position 44. That makes sense? So understanding that relationship velocity is pretty nice and easy. Displacement, though, key, S is displacement. So if they ask you for position, you take displacement plus initial position. If you have an acceleration and they ask you for a current velocity, you integrate acceleration, you add initial velocity to it. Okay, that makes sense.
Yeah.
If you want the total distance traveled, remember distance, so when I do displacement, it doesn't account for position, right? So you've got some negative and then you can go negative, and then when you get back to where you started, that's 0. The displacement doesn't care about, or the total distance doesn't care about the initial position, but you can do that. I don't want numerical derivative. I want numerical integral. All I have to do to get total distance is take the absolute value. And I wasn't quite sure how to copy and paste this, so I'm just retyping it. How to add that absolute value in. But if I take the absolute value, this will account for my distance that I traveled. That makes sense, because the absolute value will just take all parts of it, make it positive. It traveled 42.58. I think this was in centimeters. Okay. So modeling the effects of acceleration. Now, in physics, we have all kinds of constant acceleration equations. In calculus, we're not going to have constant acceleration. You can develop all of those equations by doing integrals. You can develop all of those equations by integrating the general with some constant for A. But if A is changing, you cannot use those equations. So this is not constant acceleration. It's 2.4 times time. Its rate of acceleration is increasing. So the initial velocity is 5 miles per hour. And it's accelerating for 8 seconds. So how fast is the car going when 8 seconds is up? So if I integrate acceleration, I get velocity, correct? So v of 8, I must take my initial velocity and I plug that into the calculator, how I've shown you guys. I'm not going to show that on the video, but so this is how fast was it going? 81.8. The next question is, how far did it go? This gets a little bit harder.
Yeah.
Okay. So this is where I almost have to integrate this by hand. So 2.4t, when I integrate it, becomes 1.2t squared plus c. What is my c in this case? 5. So now when I want to know how far it traveled, I don't have an initial distance because that's not where it starts doesn't matter for how far. but I need to have that integral there. And yes, you can take that integral on your calculator, but it's important that you have the understand how to do that by hand so that you can't integrate it twice, essentially. And I get 244.8. So this is kind of an odd unit. So this was in miles per hour, correct? I'm accelerating for seconds. This is miles per hour times seconds. So my time, it started with this is miles per hour per second. Then this becomes miles per hour. So I'm essentially every time I'm multiplying by time, miles per hour times seconds. If I want to convert that to like a, usable unit, no, there's 3,600 miles or seconds in 1 hour. So that will cancel both seconds and hours. You guys remember doing dimensional analysis in the past? So I'm multiplying, I want distance should be in miles, right? So I want hours and seconds to both cancel. So I'm multiplying by conversion factor. Well, seconds needs to be on the bottom, hours on top. 3,600 is 60 squared. 60 seconds in a minute, 60 minutes in an hour. And this equals 0.068 miles. Not all that far. That kind of makes sense. Yeah. Next one, this is very Idaho example. It's about potato consumption. From 1970 to 1980, the rate of potato consumption in a particular country was C of T equals 2.2 plus 1.1 to the T in millions of bushels per year. I'm sure our country goes through more, but so how many bushels were consumed from the beginning of 72 to the end of 73? So this is a rate. If I want to know a number, I integrate my rate. Because a rate is a derivative, or essentially, or rate of change is a derivative of the function. Beginning of 72 is 2. End of 73 is essentially 4. That makes sense? Because I'm doing those 2 full years. 0 o'clock, midnight on January 1st is essentially when the one ends and the next year starts. So all I have to do is integrate. I let my calculator do the work for me of the integral. That many million bushels. And a bushel, I think, is like a basket. It's actually not as many as you would think. If we're talking about America, that would be everybody gets 4 potatoes a year. Maybe 4 to 10 potatoes. And we're counting French fries and all potato chips and everything else. You're like, oh, okay, that's not very many. If you want to open your book, I'm gonna have you guys do this one with me to page 369. So, example 6, page 369. It says a pump connected to a generator operates at a varying rate. Depending on how much power is being drawn from the generator to operate other machinery. The rate, gallons per minute, at which the pump operates records 5-minute intervals for 1 hour as shown. How many gallons were pumped during that hour? So it's giving me a rate function, right? So the integral, and it's done in minutes, so 1 hour is going to be 0 to 60 of my rate function. Now, I don't know what that rate function is, but I do have data for it, correct? So I can approximate the integral with a trapezoid rule. Okay? So I notice each interval is with 5, right? Trapezoid rule is h over 2, and I double all of the middle ones. The second last one is 63, and the last one I don't double. So I took all the data from my table. Trapezoid rule is width of the intervals over 2, each width is 5. If you look at the book, they called that 60 over 12. I don't know why they did that. It's 60 minutes, there's 12 intervals. But I was like, wow, they made that harder. They're just 5. And when you plug this all into the calculator and add it up, you get 3,582.5 gallons. Because notice it was in gallons per minute. Our time was minutes. We lose a per every time we take an integral. Okay. The last thing is work. Okay. Work equals force times distance. You guys know that from physics.
Yeah.
You might not know this one, Hooke's law. The force of a spring is equal to the spring constant times the distance that the spring is stretched or compressed. Okay. The spring constant is known as the force constant. It depends on how strong and big the spring is. Some springs are very hard to compress, some you just do at the end of a pen. Or stretch. Springs also can be stretchy. So, it takes 10 newtons of force to stretch a spring 2 meters beyond its natural length. How much work is done in stretching it 4 meters? So first thing I need to do is get this K. It takes 10 newtons to stretch it 2 meters. That means K is 5, correct?
That's nice.
So my force function is 5x. Now my work can also be thought of as the integral of your force function. Okay? Because this is not a constant force, you cannot just do force times distance. Okay? The force, the further you stretch that spring, the harder the force required is, right? This one I don't feel like getting out my calculator. I'm squaring the 4, plugging in 0. 80 over 2 is 40 joules of work. Or as they said, a joule is a Newton times a meter. There's forces in newtons. Distance, every time we integrate, we multiply by that unit. Does that kind of make sense? That's 7.1.